Unit 2.2, Calorimetry. Topics in this lesson: phase changes, heating and cooling curves, specific heat capacity, enthalpy of fusion, enthalpy of vaporization. In a previous lesson, we talked about phases of matter, and when we change from one phase to another, we call it a phase change. Let's look at water. Below 0 Celsius, water molecules do not have enough energy to break free from the strong attractive forces holding them in place. They just kind of vibrate in place. If we increase the energy, if we increase the heat, now between 0 and 100 degrees Celsius, these water molecules have enough energy to break free from the attractive forces holding them in place. But they still do not yet have enough energy to overcome the attractive forces that kind of hold them close to each other. So they vibrate and they can move around, but they still stay in contact with each other. We call this a liquid. If we increase the heat some more, now above 100 degrees Celsius, the water molecules have enough energy to break free from all of the attractive forces between the molecules. They're completely free to move around, and now we have a gas. So as we increase the amount of energy, we go from solid to liquid to gas. Now a heating curve shows what happens when we add heat or energy to a substance as it goes through different temperature and phase changes. Let's look at this example. In this example, we have ice, water, and steam, which is all just water. As the heat is added, first, the solid ice increases in temperature from -20 to 0. Once it reaches 0 Celsius, it begins to melt, and the temperature remains constant. This is something you might not have noticed, but if you have water with ice in it that is melting, it stays at the same temperature until all of the ice is melted. Then, after all the ice is melted, the water increases in temperature. The liquid water increases in temperature. It goes all the way from 0 to 100 degrees Celsius as we add heat. When it reaches 100 degrees Celsius, it begins to boil, and the temperature remains constant again. If you'd like to verify this, you can go to your house and put some water on the stove in a pot and get it to boil. And you'll notice if you have like a candy thermometer or a meat thermometer, as the temperature increases, once it gets to 100 and it starts to boil, the water will basically stay at that temperature until all the water is gone. If we're able to contain the steam and measure the temperature of the steam afterwards, after all of the liquid water has boiled to steam, the steam increases in temperature as we continue to add heat. Now a cooling curve is similar to a heating curve, except it goes in the opposite direction. It shows what happens as energy is released, not added, to a substance, and the verbs are different. So we cool the steam, and then we condense it, and then we cool the liquid water. Don't worry about the part that says supercooling liquid water on this slide. We're just going to go from cooling liquid water to freezing liquid water, and then once we have liquid water frozen, we can cool the ice. Specific heat capacity. The energy required to change the temperature of 1 gram of a material by 1 degree Celsius, it's called its specific heat capacity, and it's marked with a letter C. Different materials have different specific heat capacities. Take a look at the diagram on the right. We have liquid water, solid water, and water vapor all have different specific heat capacities. Even though they're the same chemical, they're different states of matter, and so they have different specific heat capacities. One thing to note about specific heat capacities is that they're experimentally determined, and so they have significant figures. And depending on which source material you're finding your specific heat capacity in, the numbers may be slightly different depending on who published it. If we want to calculate the energy required to heat any amount of substance, this energy is given by E equals mc delta T. Energy is mass times the specific heat capacity times the change in temperature. I think the delta looks a little bit like a A, so I call this E equals MCAT to help me remember. Let's use it in an example. How much energy is required to heat 150 grams of water from 25.0 degrees Celsius to 85.0 degrees Celsius? Well, first we write our equation, E equals mc delta T. Then we substitute in our values. The mass is 150 grams. The specific heat capacity. Well, it wasn't given in the problem, and we have to kind of go back to the table previously, and we have to notice that the temperature we're dealing with here is between 25 and 85 degrees Celsius. And we should know that that is when water is in its liquid state. So we'll use the liquid water specific heat capacity, 4.18 joules per gram degree Celsius. And then we do the change in temperature. So the final temperature minus the initial temperature, 85 minus 25. And we multiply those together and we get 376.00 joules. Why did I only use 3 significant figures in my answer? Well, 4.18 joules per gram degree Celsius only has 3 sig figs. So that limits the amount of sig figs I can have in my answer for this multiplication. Enthalpy of fusion. The energy required to melt 1 gram of a material is its enthalpy of fusion, symbolized delta H fuse. Again, different materials have different enthalpies of fusion. Water has an enthalpy of fusion of 334 joules per gram. Now notice this time we don't have different enthalpies of fusion for ice and water and steam because this specifically relates to ice melting to liquid water. We have an equation that relates the energy required to melt a given substance, which is just the mass of the sample times the enthalpy of fusion. E equals m delta H fuse. Let's try an example. How much energy is required to melt 150 grams of ice to liquid water? We have our equation, E equals m delta H fuse. We substitute in our numbers, 150 grams, 334 joules per gram. We multiply them together and get 501.00 joules. Again, we only have 3 significant figures in 334, and so we can only have 3 significant figures in our answer. Enthalpy of vaporization. The energy required to vaporize 1 gram of a material is its enthalpy of vaporization, delta H vape. Again, different materials have different enthalpies of vaporization. Water has an enthalpy of vaporization of 2,256 joules per gram. We have an equation that we can use to figure out the energy required to vaporize any amount of substance, which is E equals m delta H vaporization. Let's do an example. How much energy is required to boil 150 grams of water to steam? First, we have our equation, E equals m delta H vape. We substitute in our numbers, 150 grams, 2,256 joules per gram. We multiply and get 338.400 joules. Notice we only have 4 significant figures in our answer because we only had 4 significant figures in our 2 things that we multiplied. Let's put all 3 of these equations together and solve a more complex problem. I find it particularly useful to draw a heating or cooling curve when doing problems like this to help me map out what I'll be doing. Let's read the problem. How much energy is required to heat 105.0 grams of solid copper at 25 Celsius to gaseous copper at 2,562 Celsius? Note, copper melts at 1,085 degrees Celsius and boils at 2,562 degrees Celsius. So if we map this out, First, we start with solid copper, and we have to heat it from 25 degrees all the way to the temperature at which it melts, 1085 degrees. Once we get there, we melt it, and then we have to continue heating it. We heat the melted copper until the temperature at which it boils, 2562 degrees Celsius. Once we boil it all, then we'll have gaseous copper at 2562 degrees Celsius. To heat something, we use E equals MCAT. So we have 105 times 0.38 joules per gram degrees Celsius. Our change in temperature is 1085 minus 25, and we get that product. Next, we have to melt the solid copper. We use E equals M delta H fuse. We have 105 grams and multiply it by 134 joules per gram. Next, we have to heat the liquid copper. E equals MCAT, 105 grams, 0.38 joules per gram degree Celsius, and then 2562 minus 1085. We multiply those together to get our answer. And finally, now we need to boil the liquid copper. E equals M delta H vaporization. 105 times 5069 joules per gram. We get that answer. All of our sub-answers need to be converted to the proper number of significant figures. So we have 2 sig figs in the first one, 3 sig figs in the second one, 2 sig figs in the third one, and 4 sig figs in the fourth one. And then we add them all up, and we have our grand total of, 644,300 joules.